All right, everybody, I think it's just about that time. It's showtime here. Thursday morning. Welcome, and I hope that you're having a good week so far. It's good to see all of you, and thanks for being here, of course. Always happy to have you. And it's hopefully finish chapter 4 today. This really long chapter. The tail end of the chapter actually goes pretty quickly once we kind of get these ideas of spanning sets and linear independence under our belt. Sort of everything else it usually starts to flow a little bit more easily. So I'm hoping that'll be the case. And so let's see if we can kind of review where we were last time and finally start putting things together. By the way, thank you so much for the homework you turned in on Tuesday. I realized this morning I hadn't been it's been a couple weeks since I actually posted solutions to homework, even going back a couple of assignments. So I got that all updated on Canvas. So whenever you get your homework back, please do remember that the solutions are in Canvas, and you really should close the loop on your understanding of those problems by checking the solutions, even if you got a perfect score, because of course my grader is only checking certain things, not necessarily everything that might have come up. So it's helpful, I think. If I was in your shoes, I would do that. I would look at the solutions and kind of check them against what I have, especially if you hadn't had a chance to ask me about it, just to make sure that you were on the right track. But anyhow, let's just remember this idea that we were talking about on Tuesday, which is the dimension of a vector space. Okay, it's one of the most important numbers that we can associate with a vector space. This is classic vector space theory here. And this number is just how many vectors would be in a basis for V. Now remember that a basis, we defined that last time, probably the most important concept in a vector space. A basis is a set of vectors that is both a spanning set and Li. It is both of those things, right? So we're going to practice that in a second, looking for bases for vector spaces. But one thing we did mention on Tuesday is that although you can have many different bases for a vector space, they will all have one thing in common, which is how many vectors are in that basis. Okay, so you can't have two different bases with two different numbers of vectors. So this is a well-defined number, right? It makes sense for any vector space. How many vectors are in any basis for V? That's the dimension of G. Okay, so there's your definition. And I wrote down, we talked through a few of these very familiar vector spaces on Tuesday, and you should know these cold. Like literally you wake up in the morning, you should just, these should be in your head, right? So the dimension of Rn is just n, right? The dimension of Pn of R is just n plus 1. I always like to tell people if it's something that's important on my mind, I'm going to be thinking about it while I'm in the shower in the morning, right? It comes up in my head random times and places, things like this, right? The dimension of the n by n matrices, well, that's always n squared, right? And the dimension of the m by n matrices is m times n, okay? Of course, these are not the only vector spaces in the world, but these are 4 of the most common universes. You've already been noticing this in the homeworks, right? That we're typically working either with Rn or with matrices or with polynomials or something like that. So these are very, very familiar vector spaces. Now, one of the reasons why it's important to know these numbers cold is the important observation, these 3 points that I've made here on the recap on the left side, which is that if you know the dimension of V in advance, I say if, because, if it's one of these, you better know it, right? But there could be other vector spaces where maybe we don't know the dimension in advance. But if we know the dimension of V in advance, and somebody comes along and proposes K vectors to us. Say V1, V2, V3, they hand us those vectors. They might ask us a question like, well, are those vectors a spanning set? Are they Li? Are they both? Or are they neither? Right? That's a typical question. Now, we've already looked at that a couple of times on Tuesday, but this three-part sort of summary is really useful. If K is bigger than the dimension, and again, that requires you to know what the dimension is. But if I give you more vectors, guys, than the dimension of V, then they can't be Li. No chance. It's game over before you even take a breath, right? They cannot be Li. They might span V. That's still kind of up in the air. So in that case, we have to spend a little more time and think about whether they would span V or check whether they would span V, okay? The opposite scenario, if K is less than the dimension of V, okay, that means I did not give you enough vectors to begin with. Well, then there's no chance that they could span V. They cannot span V if it's not enough vectors. They might be Li. Again, the jury is out on that part. You would have to test it in the way that we test Li normally, right? And we're going to practice that again in a minute. The last case is the most promising one. If K is equal to the dimension of V, well, that's in other words, somebody handed you the correct number of vectors. It's still not guaranteed to be a basis, though. And so what we can conclude here is that that set S will either be both or neither, right? And what you can do is configure the vectors, as we usually do, into the columns of a matrix. And in this third scenario, the matrix will be literally a square size. And if it's a square size, we can take the determinant of it. And to decide whether it's both or whether it's neither, it just comes down to whether that determinant is not zero, which remember is a good thing. That means the matrix is invertible, and that means that the set S will be a basis, right? Or it could be really bad situation if the determinant is equal to zero. That's a bad thing. That means the matrix is not invertible, and that means that this set is going to be neither Li nor a spanning set. So this is what is on this board, my friends, is like such a good little overview of these last couple of sections and kind of a good summary of some of the points we've been making. So I encourage you to either write it down or take a picture of it, because you probably will want to look back at this again. Any questions on this summary from Tuesday so far? Let's practice it on a couple of warm-up problems. Let's just kind of get our minds going here this morning. It's a foggy, dark morning out there. I gotta get the cobwebs off and see if anything makes sense today, right? So let's just try a couple of examples. This is a typical question from midterm 2, right? Which, by the way, is 2 weeks from today. So this is a good time to really start locking in. Given a set of vectors, I can ask, is it a spanning set? Is it Li? Is it both? Or is it neither? So here's the example. V is P2 of R, and S is this set of 2 polynomials right here. Okay? So what I'm going to recommend that you do is start by asking yourself if you know the dimension of V. Does anybody know the dimension of this vector space P2 of R? It's 3, right? Using the formula right here. P2 of R, the dimension would be 3. And then what I would probably also recommend that we do is we come over here and we figure out, well, what's the K value? How many vectors did they give us? Anybody want to tell me? 2. You literally just have to count them. There's 2 polynomials there. So K is 2. All right, so that means K is less than the dimension of V. K is 2, the dimension of V is 3. That's the second case here. So I already know, my friends, I already know that S, what's it say? Cannot span V. This is case 2 in my little recap over here, right? So S cannot span V in this case. So we already know that it's not a spanning set, and of course that means it can't be both. So out of your 4 choices here, guys, what I hope that you're recognizing is that you can always cross off 2 of the 4 choices immediately by just doing this analysis. What is K? What is the dimension of V? From that, you can immediately rule out part of the answers. It's simply not enough vectors, right? 2 vectors cannot span something that's 3-dimensional. Remember, the dimension is kind of a measure of the size of the vector space, right? V is a big enough vector space that if you want to be able to make all possible linear combinations and get everything in V, you'll have to have linear combinations of 3 vectors. You can't get away with less than that. So this is just not enough vectors to span it. It's just plain and simple. Okay. Now, the second part, though, is we're still interested in knowing whether the vectors are Li or not. Okay, so I'd like to address that. So do you remember how we test Li? It says the vectors might be Li. So the way we would test Li, I'll just say check Li here. This part, we actually have to get our hands dirty a little bit and actually calculate this. So what I would do, if you remember, we make a matrix, right? Everything in this class is put it in a matrix. I would just put these coefficients into the columns of a matrix. So remember that the vectors go column-wise. So 1, -2, and 5. And then the second vector would be 1, 1, and 7. And do you remember what we augment the matrix with when we're checking for the Li part of the question? Zeros, all zeros, exactly. The number symbols, you remember the number symbols also. We would do that if we were checking the span question. But we don't have to check the span question because we already know that these vectors don't span V. Okay, so at this point, we just have to do our EROs here. The first row looks super good already. Just going to leave that the way it was. I'm going to take 2 times the first row and add that to the second row. 2 times the first row added to the second row gives me 0 and 3 and whatever. And I already know that I'm not going to have any free variables, right? Because there's already pivots in both of these columns. But just for the record, I could go ahead. I will just skip the details. You'll end up getting a row of zeros out of this calculation. This is an example, guys, of a matrix that is tall and skinny, right? It has more rows than columns. So it looks tall and skinny. So you're not surprised to see this kind of a result. By the way, sometimes people get a little bit overexcited about rows of zeros. Here we have a row of zeros on the bottom. I just want to remind you again, rows of zeros really don't tell you anything. Those are really just worthless equations. But remember, we have unknowns here, which we can remind ourselves, usually we were calling these C1 and C2. That bottom row just says that C1 times 0 plus C2 times 0 is equal to 0. Well, that's worthless information, right? If I tell you that C1 times 0 plus C2 times 0 adds up to 0, right? That absolutely tells you nothing about what C1 is equal to or what C2 is equal to, right? This is already just automatically true. So don't read too much into that. I do see sometimes people like to get obsessed with, oh, I have a row of zeros here, that must tell me something. Not necessarily, not necessarily. So just keep that in mind. So what are we going to conclude here about, are these vectors Li? They are, right? No free variables, so they are Li. So the answer to this first warm-up problem, let me just add that over here, no free variables. And that implies that the vectors are Li. Before I go on, are there any questions on that first example there, guys? Audrey?
What the C1 action?
The C1 is just a constant of some linear combination. So where this all came from, like where the matrix came from, is you have C1 times the first vector plus C2 times the second vector. And in the case of Li, we are setting that equal to 0. And we're just asking what are the constants? And if the only way to make this cancel out to 0 is by putting zeros for the constants. That's the definition of Li. And in this case, yeah, we do conclude here, maybe I should have said that here. So this implies here that C1 equals C2 equals 0. We could add that as well. Yeah. Good question. Was there another hand, Alex?
Yeah, sorry, how did you get the zeros in the third row?
On this row?
Yeah.
I did several EROs in my head
Oh.
and I didn't show all the work just to save a little time. Yeah, good point. Yeah, so this is, guys, I'm starting to go a little faster with EROs these days. You might have noticed that. I'm trying not to get bogged down on that. That's not really the most important point of what we're going to be doing. By now, everybody should be able to do EROs pretty easily. I do want to make another remark here before I go to the second warm-up problem though. So you could add this into your notes as well if you have a spot for it. A quick remark about Li. I think I might have forgotten to state this the other day when we were going over this, maybe last week. When you only have two vectors. Okay, I'm going to start over again because that's actually really important. When you only have two vectors, there's an easy way to look for Li. I know we have this whole thing where we put them in the matrix and we do the EROs and all of that. However, the remark is that if we only have two vectors, that set of vectors is Li. Just in case I forgot to say this last week, I just can't remember right now whether I told you this before or not. They will be Li if and only if V1 and V2 are not scalar multiples of each other. Does anybody remember, did I say that before? This is only for two vectors. If I have three vectors or four, I think there was a true false item on the homework that you turned in Tuesday, which said that if you have three vectors, would it be true that they have to all be proportional to each other? And the answer to that would be false, right? For three vectors, it's not the case that to be Li, that they would have to be not proportional to each other. So this is only for two vectors. So here we have two vectors and they're not multiples of each other, right? So in that case, if we have two vectors that are not scalar multiples of each other, we could have just said that they're Li just by looking at them. Okay, now if you forget this remark, it slips your mind or whatever, there's nothing wrong with doing the matrix. Just what we did here, it's not that bad, right, to write that out. But I just want people to be aware of this. If you have two vectors, please do not try to extend this to three vectors or four vectors. I can give you three vectors. Here they are. They're all in the plane of the whiteboard, right? That's three vectors in a two-dimensional space. They are definitely LD, but none of these are multiples of each other. They're all pointing in different directions. So be careful about trying to use this idea for more than two vectors. I keep harping on it because every semester somebody does it. And so just don't let it be you. Let it be somebody else this time that overextends that idea. Okay, so anyway, just wanted to get that remark into the notes as well. Any questions? Everybody okay? Starting to get the hang of all this? I think so. I love this stuff. Let's take a look at the example B here. This time I'm going to go to a matrix situation. So I'm going to take M2 of R, and I'm going to take these three vectors right here. Okay, so can somebody tell me in this case, what is the dimension of V? 4. It is 4 according to my list over here on the left. So that is a 4-dimensional vector space. And what is K on this problem? 3. Only 3. Okay, so actually, this is very similar to the first example. We are in case 2 again. S cannot span V. That's case 2. So we have exactly the same setup here. And so the only question is, are the vectors Li or Ld? And I'm wondering if anybody can tell me without, we could set up the matrix again. But can you tell me without setting up the matrix? They have to be LD, don't they? Do you see why? S is LD, right? LD since I rigged this a little bit. Blake? Yeah, the first and third vectors, I kind of tried to make this pretty obvious. The third vector is already a multiple of the first one. So I know that if I took 5 times the first vector and then subtracted the third vector, that I would get 0, right? So we think of this as v1, v2, and v3. Then I can just see directly that there's a linear dependency here, right? So this is a linear dependency. Right, so I have a couple of vectors here that are scalar multiples of each other, so they of course have to be LD. Okay, so the answer to this one then would be neither. This is a case of neither. These vectors are not a spanning set, nor are they Li. They're actually neither. Guys, neither is an option that is always on the table for any example. What I sometimes see people do is they'll tell me, oh, K was not equal to the dimension of V, so it can't be both or neither. And they'll cross off the both option and they'll cross off the neither option. But actually, if K does not equal the dimension of V, it just means we're not in this case down here. But we still have that, one of the two properties fails and the other one might also fail. It's only that if we are in this case, then the correct answer has to be both or neither. But if we're not in this case, we shouldn't conclude that it can't be either of those things. Neither is always on the table as an option. Let's do one more. Let me come over here. We'll do one more and then I'm going to let you guys practice. We've got some group work today. Let's take V to be R3 this time. And let's take S to be the set 1, 8, 2, comma 9, -1, 4, comma 3, 6, 6, and comma 7, 4, -2. Do one more warm-up problem today, and then I think we're gonna hopefully have the idea here. So S consists of 1, 8, 2, 9, -1, 4, 3, 6, 6, and 7, 4, -2. So let's give it a shot. Let's start off with, what is the dimension of V this time? It's definitely 3, right? It's definitely 3. And what is the value of K this time? 4. 4 vectors, right? 1, 2, 3, 4. So K is 4, the dimension of V is 3, so that's actually case 1. K is bigger than the dimension of V, so in this case, we can say that S cannot be Li. Do you notice how the conclusions here are always negative conclusions? S can't be this, S can't be that. Right? We're drawing the negative conclusions very easily, but we're never able to affirmatively say positive things without doing more work. I can't say right now whether S spans V or I just know it can't be Li. So this is case 1 of our important remark over there at the recap. And so now I want to test. It says it might span V, so I'd like to test that. So we know how to do this with a matrix, right? We're going to make a matrix here. We're going to put the vectors into the columns of a matrix. So 1, 8, 2, 9, -1, 4, 3, 6, and 6, and 7, 4, and -2. So there you have it. And what am I going to augment this matrix with? My number symbols, right? My hashtags. So I put my little hashtag number symbols here in the far right column for checking spanning sets. That's how we do it. Okay, so I like the first pivot is already in the top left corner here. So let's just see what happens. I'm going to recopy that first column or that first row before I do anything else. And oh boy, I don't know if I chose my numbers very well here. I'm gonna take -8 times the first row and add it to the second row. So I'll get a 0 here. I need to get that 0. So this is gonna be a -73 of all things. And then -24 plus 6, that's -18. And then -56 plus 2 is -52. And this just stays as a number symbol. So my numbers aren't very nice in this matrix, unfortunately. If I take -2 times the first row and add it to the third row, I'll get 0, -14, 0, and -16. And then we still have a number symbol here. Okay, and that will end up being a pivot. I don't mind that these numbers are a little messy because it's actually good to practice what do you do, because we don't actually have to get too deep into this. All I care about is whether a pivot goes way to the far right column or not. And I can figure that out without hurting my head too much on these calculations. I can already see that if I multiply the second row by what? -14/73 and add it to the third row, that what will happen is, you take a look. I don't actually have to solve the system. I just have to figure out where are these pivots going to be. So I don't mind that these numbers are a little nasty because I know that I'm going to make a 0 there by using A23 of -14/73. And this is not going to be 0 and 0 here. That's my point. So I'm going to put a question mark there because I don't actually want to calculate it. Okay, I have to take -18 and multiply it by -14/73 and add it to 0. Well, that's not going to be 0. So I'm going to just assume that I've done it right and that that's going to be a pivot. Based on this calculation, based on how those pivots have ended up, we don't have to go any farther. Can you tell me, will these vectors be a spanning set for V? Yes or no?
Yes.
Yes, they will, right? There's no pivot in the far right column, so yes, they will. So this is good. S is a spanning set. Okay, so in this case, we have a spanning set, but the vectors are LD. But again, you know, out of the 4 multiple choice options, we cross off LI right away. We cross off both right away. Gilbert.
So as long as there's no pivot in the far right column, it spans.
You got it. That's how that works. Absolutely. Nathan?
By doing this, we also just confirm.
Exactly. Had we been actually checking LI the old-fashioned way, we would have augmented this last column with zeros instead of number symbols, but nothing else would have changed about the calculation. And we can see that the fourth column would have been aligned with a free variable. Free variables are bad. That means the vectors are LD. If we had actually wanted to come up with a linear dependency, well, then we would have had to actually work out these numbers and like set up the free variable and do back substitution, and that would have been messy. Okay, so luckily we don't have to do that here. Okay, other questions on this? Yeah, go ahead.
To check if it's spanning, that's when you use the number symbols, and then to
Yes,
check for allies to zeros.
that's
What was-
right.
What was the case when you used both?
Well, if I want to just test them both directly
Absolutely.
at the same time, I could put 0/number symbol. Absolutely, yeah.
Thing. Find it linear dependent and full.
Oh, so in this case, I could have said, if these vectors are LD, could you replace the set with a linearly independent set that has the same span? Yeah, so Audrey's remembering the idea of, okay, the fourth column is unpivoted. So I want to get rid of it to remove the linear dependency, and getting rid of it effectively means getting rid of that. If I had gotten rid of that, then these 3 vectors here, just these 3, skipping the fourth one, just these 3 vectors, these would have been a basis. They would have been both, right? Because they're already, if I take out that last column, we still don't have a pivot in the far right column. They're already a spanning set. And now they would also be LI. So just these three, be careful if you're taking notes on this, that you don't include the fourth vector. Just these three, this is a basis. Just that much is a basis. Yeah, Alex.
There was also questions on the homework, which is what I was talking about.
Okay.
You were given vectors and you had to find like a spanning set that wasn't all those vectors. I think something like that, and I thought that's what we do for that, where we find the pivots and then we get rid of one vector and that would be the spanning set. It was like given set of vector B, find spanning set.
Find a spanning set for V. That's totally different thing than what we're talking about here. Finding a spanning set for a vector space is where you write down the form. We're going to practice it also in the group work. You write down the form of a general vector in that vector space using variables, and then you bust out those variables, and then you just list the vectors that are left behind. So that's not tied up so much with the dimension theory and this sort of three case scenario here. But it's also a very important thing to be able to do. Other points? These are good questions. All of this, these examples hinge on knowing these dimensions. So we have to really, that's why I keep saying, we've got to learn these dimensions. If we don't know those dimensions, then of course we can't benefit so much from those remarks. But then you might be wondering, that leads to an interesting question. What if I have some weird vector space that I don't know the dimension of ahead of time? I think I'd like to talk about that for a minute. I got the perfect example to do it with. Because there are vector spaces that we don't know the dimension of ahead of time. So let me just do, so I'll just phrase that as a question. What if we don't know the dimension of V in advance? Right. What if we don't know the dimension of the vector space in advance? Well, in that case, you sort of have to try to figure out the dimension first and foremost. Well, let's take a look at an example of a scenario where that might be the case, where you don't know the dimension ahead of time. So here's an example of that. Suppose I give you a matrix A. I'm going to write the matrix here. Let's take the matrix 1, 2, 6, 2, 1, 6, 0, 1, 2, and 1, 0, 2. So I'm going to give you this matrix, and I would like to find a basis for the null space of A. So obviously, if we've never seen this matrix before, which we haven't, we're not going to know like what the dimension of it should be. We don't know how many vectors should be in a basis for it. I know how many vectors should be in a basis for Rn. I know how many vectors should be in a basis for Pn, but I don't know how many vectors should be in a basis for this because I've never seen this matrix before. This is like, what am I going to do here? Okay, well, you're absolutely right. If you haven't seen the example before, then you actually have to find the null space of A first, and then figure out what a basis for it would be. All right, so to solve a problem like this, let me just remind you here that the null space of A is really just a system of equations where each equation is equal to 0. So the first step here is we have to find the null space of A. So I'm going to do that actually. We're going to augment our matrix with a column of zeros. By the way, I sometimes hate to talk about things that could potentially confuse people, but then somebody was going to ask me. You might notice that what I did here by augmenting with a column of zeros is not that different than what we do when we test for Li. When we have a set of vectors and we're testing whether they are Li or not, we lay the vectors in the columns of the matrix and we augment it with, not with number symbols, but with a column of zeros. And that's exactly what we seem to have done here. We took our original problem and we augmented it with a column of zeros. So people start getting this confusion between null spaces and Li. Because in both cases, you're putting this column of zeros on the far right column. My recommendation is to not like if you want to come to my office hours, we could like flesh that out a little bit. I could like explain like what's the connection there, but I really think it's better to not think of this in the same breath as the concept of Li. They're really two different things, okay? But this is how you find a null space. You're just going to, you have these unknowns here. One thing we could do is instead of calling the unknowns C1, C2, and C3, which is what we would have done for the Li question, let's call them X, Y, and Z. So this is a system of equations, right? This is a system of equations, you know, X plus 2Y plus 6Z equals 0, 2X plus Y plus 6Z equals 0, Y plus 2Z equals 0, and X plus 2Z equals 0. That's the system. And we're just putting it into this matrix here. That's basically what we're talking about. I'm going to circle this pivot up here in the top left corner. And if you guys will let me just skip the EROs and give you the row echelon form, that might save us a little time here. So what I would end up with, guys, I will just ask you to trust me on this. If I permute the third row to the second row, I'm going to get that. So I leave the first row alone. I permute the third row to the second row. It turns out that if you do the EROs, all of the other rows just become all zeros. And again, I just want to remind you, don't read too much into that. Getting a row of zeros is basically you're coming up with worthless information. So it's no point in like overanalyzing the rows of zeros. Really, the meat of the problem here is in the first two rows. So as you know, we have here a free variable, which is Z. I'm going to call it T for the time being. And then if I back substitute, so basically if Z is equal to T and I back substitute into this equation, I can solve for Y. What will Y be equal to? Negative 2T, very good. All right, and then using both of those values, I can go back to the top equation. And if I put in Z equals T and Y equals negative 2T, and I solve it for X, I should get, I think it's negative 2T again. So I'll let you guys check those details. So this is just chapter 2, literally a whole month ago now that we were learning how to do this. Just do your EROs, get the row echelon form, introduce free variables, and solve it by back substitution. And so my null space of A, not doing anything new, my null space of A is just negative 2T, comma, negative 2T, comma, T, such that T is a real number. This is how we would write it. This is how we would write it. And so that's what the null space is as a set of vectors, as a subspace. By the way, I just remind everybody that the null space of A is a subspace of R what? Just remind ourselves here. In this example, the null space would be a subspace of R3. Excellent. R3 because, well, first two reasons. One is I see 3 slots here. Okay, if there's 3 slots, then that means that these are vectors in R3. And in addition to that, we can just remember that looking at the size of the original matrix, which in this case has 4 rows and 3 columns, you have the M and the N values here. The null space is always a subspace of Rn. So it's R3. So although the dimension of R3 is 3, I don't know what the dimension of the null space of A is because it's a subspace of R3. It might be smaller than the whole R3 is. And in fact, if I asked you to give me a spanning set for this, what would you probably do next? think we need to do that. We're almost already looking at a spanning set here. What's the one little thing we have to do to get the spanning set? Alex?
Sure, no.
Hold on, to
Bust out the variables, right? So we write down the form of a vector. That's step one. Step two is bust out the variables. And step three is make your list. Well, if I bust out the variables here, I'm just going to be left with -2, -2, and 1. So I'm going to go ahead and do that. I'm going to drop the t from the notation. I don't need to keep the free variable anymore. I just write down this guy right here. And this is a spanning set for the null space. But you know what? It's also Li because it's only one vector. You cannot have a linear dependency if you only have one vector. So this is your basis. This is your basis. So this is the basis for the null space of A. That is actually the answer to this problem. That is your basis, just that one vector. And so in this case, the dimension is only 1. It is a one-dimensional subspace of R3. Let's actually write that down. So here, the dimension of the null space of A, right, is equal to 1. It is a one-dimensional subspace of R3. So null space of A is a one-dimensional subspace of R3, which is the Rn in this case. But again, just looking at the original matrix, I wouldn't have known that it was one-dimensional. I had to do some work to figure that out, didn't I? I don't just see it straight off the cuff. Looking at this matrix, I actually had to do the EROs, circle my pivots, set up my free variables, back substitute it, bust out the variables, and then I have my list, and the list has one thing in it. And so therefore it's one-dimensional. Alex.
Is there only gonna be, like, I guess, one vector and a basis for one matrix? There can't be more than, right?
What if I had more than one unpivoted column? Remember, actually, you're bringing up a really good point. Can I talk about that for a minute? Okay, I'm going to talk about that for a minute. Before I do that, I want to make a quick definition here, guys. By the way, in case you're wondering, we're kind of covering 4.8, 4.9 right now. They go together hand in hand. The nullity of a matrix. This is the thing I want to define. So given any matrix A, which is M by N, the nullity of A is the dimension of its null space. I'll just say the dimension of the null space of A. Okay, so again, just to write it as an equation, the nullity of A is just dim of the null space of A. This is a new word that is very common in the theory of matrices. The nullity of a matrix, it's just the dimension of the null space. But I want to explore Alex's observation for a minute in a little bit more detail here. In this example, that dimension was 1. So the matrix A over here has a nullity of 1 on this problem. Alex was sort of suggesting, well, maybe it's always going to be 1. And I'm trying to push back a little bit and say, well, wait a minute. Maybe the dimension of this null space could be a different number. Can we think about why did this nullity turn out to be 1? let's just think back through what we did over here for a second. I got a couple hands up here. Gilbert, go ahead.
Cause there was only one free variable.
Because there was only one free variable, right? Because when I did the busting out part, awesome. Because when I did the busting out part, right, I only had one variable to bust out. Now, why was there only one free variable? There's only one free variable because all of the other columns had pivots. Right? So there was one unpivoted column here. So maybe we could just make this as a remark. The nullity of A, right, is equal to the number of free variables. Let's just say in, yeah, well, I'll just, in the row echelon form of A, I guess I could write that. It's kind of the number of free variables. But remember, guys, every variable is either free or leading. Every variable is either a free variable or it's associated with a pivot. In this case, Z is free and X and Y are both associated with pivots, right? So we could also rephrase this as just saying this is the number of unpivoted columns of the row echelon form of A. So it's just how many columns don't have pivots. Because every time you have an unpivoted column, you have a free variable. Okay, are you ready for the absolute easiest theorem in all of linear algebra? I'm going to give it to you right now. This is the easiest theorem in the entire world to understand. Would you agree that every column of your matrix is either pivoted or not pivoted? All right. The unpivoted ones are lined up with the nullity of the matrix. The pivoted ones, when I count how many pivots I have, was there a name for that? The rank. It was the rank. The number of unpivoted columns would be all of the columns except for the pivoted ones, right? So I'm going to say n, which is the total number of columns, minus the number of pivoted columns of the row echelon form of A. And that is simply n minus the rank of A. So the most simple theorem of all in linear algebra, this is a for sure. I mean, everything we're doing in here is important. I write important next to everything, but this is extremely important as well. I don't waste time on things that aren't important. The rank nullity theorem. Do you see, guys, how this equation works? Take a look. There is a relationship between the rank and the nullity of any matrix. And here it is, my friends. The rank of A plus the nullity of A. If you add those numbers together, you get n. You get n. And all this is saying is every column either was pivoted, which means it was over here in the rank category, or it was unpivoted, in which case it was in the nullity category. Okay, so if you take any matrix whatsoever, n is an easy number. It's just how many columns do you have? So in this example, 3, right? And the rank nullity theorem in this example says that the rank is 2, the nullity is 1, 2 plus 1 equals 3. Okay, that's literally what the formula reads out to be. So this is about the only thing I want to cover out of section 4.9. It's just this result here, and you could probably almost explain it to somebody on the street. That is basically take your matrix. How many columns do you have? Okay, every one of them either ends up having a pivot or doesn't. And that's how those two numbers are going to be related. Yeah. Alex, did I answer your questions pretty well on that? Okay, sweet. Any other, yeah, Nathan.
So if there's no pivots, then the nullity is 0.
If there's no pivots, the rank is 0. So the rank is the number of pivots. So if there's no pivots,
I'm sorry, I meant if there's no free variable.
If there's no free variables, the nullity is 0. Absolutely right. That's absolutely right. Okay. Other questions on this? Okay, if not, before we take a little break today, I have a group work. I'd like to have you guys practice a little bit on some of these things we've been talking about this morning. I'm gonna send this down the line here. And we should have plenty of markers all over the place. I'd love to get you out of your chairs, find a couple people to work with, doesn't matter who. Just you can skip number 1A. I kind of crossed it off already here, so you can just go on to 1B right away. And I'm gonna give you a hint. And for you guys. And we can erase anything up here, I think. And do that. Horrible. First step is to stand up. Once you've done that, you can start reading the questions. Thanks, Audrey.
You guys wanna go over there? Yes, yeah, go, run.
Okay, let's go to town. Come on down, guys.
Good for a microphone. He doesn't take the head out. We're doing 1 week. Getting all those items like that is fun. Great.
Like general form. Yeah.
So you're gonna write down the form of that 2 by 3. Build yourself up like a vacation. And then you start filling in the edges. That's over there.
Oh, look at the aim.
Yeah, 2 rows, 3 columns.
So, yeah.
And I think that works pretty good. Okay, so C.
We're adding the row to.
Yeah.
80.
Oh, that's perfect.
I thought you wanted to.
Mine makes sense to you guys? Mine is the.
Oh, there's separate, okay, I mean, it's kind of.
You remember what now? It's like the homework. Yeah, it's like the homework, yeah. So. We take turns.
We're doing it in class. I was just like looking to like A, B, C, and I just put like, oh, A, B, C was. Yeah, but then you have to say if everything's. So you do the thing with the augmented with numbers.
But then if you did that,
I think it's good.
yeah. Like doing the arrow.
Is that on this one? I mean, this one,
My agenda winning the end. No, that was.
Stay keen on the PROs. Work you need to.
I mean, they're only like one. Right, so.
Well, they had this one little dude and he would like, he's on the line, but he could chuck to other people. And I'm just about to get rude. No, listen to what you're doing.
Yeah, there's this one guy I know, Ethan, who plays, he's like short Filipino. But I know he. Like, I know how to like.
No.
You like that.
We just did him for.
Your team.
China. Right?
Like the.
Six. What's the day?
The lesson, I think that's a lot.
It goes down and side to side, so there's all these stars that go each other. It goes over, right? And you guys always be thinking about it, you just think. What's the size of that matrix? It's where. There's a big size. You can also go back. And how do you raise them? It's just gonna be. There's just one, it's a three. Problems. So if it's zero, it's. Not zero, it's zero. Everything goes wrong. So the first thing is. Your team's. That's fine, yeah, so it'll be the four of those together, and I'm happy with it. Yes, so, good job. And writing this down, this is the key steps. How to determine which one being. You can make the letters. Tricks, I usually just say left or right. So I just put anything here, anything here, and said, okay, this one has to cancel those two. There's anything here, this has to cancel those. Yeah, exactly. You can't just write it like, oh, this is not incorporating the constraint that the rows add up to zero. So I like the runs here. This is. I mean, I could, well, if I wanted to. I could do this. I guess I it's what I'm saying. This is my Anybody need help? No. Good job, good job.
Anybody need help?
I wanna be go.
Learn not to be fine.
Look at these.
It's not.
What? But that makes like V is 4. V is 4, that's this 5. Yes, that's case 1. Yeah.
How's it going?
That absolutely. Not both, right?
Yeah, I think family is a beat. And then it's
It's a wide family. Can't be honest. It doesn't stand back.
Because they really nothing flat, it's just throughout in the whole year, you know, like they always say zeros and they always say numbers and they. I guess to like differentiate, looking at possibly that would be boring. Always say good morning. Yeah,
Yeah, there's like enough minutes. It's like.
All means, all zero, no means
So that's why you just.
Always stay the same.
Technically, if it's a zero, it's not a pair.
What?
Oh, okay. 2-0.
So it's. Yeah.
Why not?
You just already in the second row, just so you have it. They would tell you.
You can already see where it's gonna be, like, where the filters are. There's gonna be two big variables. It wasn't gonna change what. Good? Yeah, so we get rid of those four columns, right? Like the column is gonna be variable. Oh, shit. Yeah. Okay.
Are you done? Yeah. You can take a break.
So what's special? It's a knee-jerk reaction for me. If I see a square matrix, I'm like, ooh, I can take the material of it. And the material tells me so much. It tells me that if I did the EROs, which is a lot of work, but if I don't have time to do that, then whether I'm getting.
I mean, you can basically already tell that you're really.
Tells me whether if it's going down the diagonal, or whether there are any row zeros, which would be giving me a free variable.
Though it does.
So that's what this note says.
Oh, yeah.
Is this. So we go. This say that basically you get a row, it's gonna be like. Nothing going. Especially for the 3x3, since we have this arrow method, you can literally.
It's not.
No, this was case one.
No, it's not.
No, this is case one, so it's not a lie exact, I mean, it is. His attention for just a second. I'd like to give you a break. If you need to take you can keep working if you want, but we're gonna take a break for roughly 7 or 8 minutes here. If you wanna go get some fresh air, a drink of water, anything, whether you're finished or not, no big deal away. Looks like people are kind of getting the idea here.
So it can't be LD, so it has to be LD. And we were just checking.
So how do we, remember what he said? He said it could be,
I know.
just because he's never mentioned either case within the year, it could still be.
Correct.
Specified.
So
It's not-
it's
really-
It's not LI and it doesn't span.
That's what I'm saying, how do we know? And how do you know it's not LD?
Because if it's not LI, it is LD.
Or D.
I'm a.
No, it's either LI or it's LD. There's no neither.
Yeah, just with, it's, yeah, every set of vectors will either be Li or it will be L. So when K does not equal and equal the dimension of V, such as in this case, sometimes what students in the class oh, well, we're not in the case where it's both or neither. But they'll say, oh, since the K does not equal the dimension, so they look at my case 3 and they say, oh, well, we're not in this case, so it's not both or neither. But what I'm saying is, we're in these cases, neither.
Yeah, in this case, it is neither.
It is actually for both. Yeah, exactly.
When is it?
When it's not LI. LD just means it's not LI.
LD just means that there's a free variable, and right, so if you have your row echelon form here, you have a variable here. It's L. Yes,
When it's not LI, it's LD.
it is LD.
You don't have any.
You can use the
I thought they like,
spanning.
and then my.
The logic of the question's phrase. I'm sorry. No, you're all good. You're all good.
We basically say it's LD the second we realize that it's. If it's not, Elijah has to be.
That's it.
That's it, yeah.
Good job, good job.
Is this your handout?
Edible glitter.
Website thing for.
Thank you.
Like, my partner. It is, it's in the sixth, three of us did slides, three of us did, the school of website thing. Because basically the whole, this project that was. Like how it was. So we have to think interactive, and so I was like, oh, what if we do a website where it's a choose your own adventure? Well, I could take the site, so like.
Can you schedule it?
And so we were basically all doing it last night. And my partner is Joey's. They're parts of this.
Like this. Sandwich. I want a breakfast. Like a adult flexible. I think I have like one of those like field shirts.
Did somebody leave their pencil up here, this mechanical pencil? Somebody was working up here? It's not mine. I don't use these things. I tend to press very hard. I always bust the lips. It's like, I have to use I have to always use a pen for everything. I just hope I don't make a mistake.
No, I was like so happy for like 3 or 4, and then I got to like 5, 6, and I was like ready to predict. Oh, because they were nasty. I don't know. And I was so hungry, so it's like when I'm hungry, I'm like, well, I'd eat any. So why do I feel like I'm it's so weird. But yeah, like sad. That's New York bagel had really good muffins too. They have like a cinnamon. No, it's not like. I said slide. Not words. Like I did the worst like bus. This is gas. Let me see how far it was. Are we just moving on? I have no idea. Oh, probably. I think we're just moving on. Are we really? Yeah. But there's extra space for paper if you want to do it. Yeah. I already put my order. She said, no, I think we're good. Should we schedule for 11:45 or 12? The most important part was that we understand the map, not that we do the map. That's not a contradictory, but. No, but that's true. It's true. It's true. Do you understand? Yeah. I'm scared because I'm gonna test and other people next to me are gonna ask how I did. I don't want to tell them because I know I did bad. And I know they did good because they're smart and they study their asses off, and I'm stupid. And I don't study my head. And we did practice. Let's talk about the quiz too. Okay, in our class, only 4 people got 15s out of 15, and only 4 people got 14s out of 15. And they were the ones who got the 14s. And then I'm like, here with my 7. I was like, I don't want to think that's against them. When you're here for 14s, first. Like some people just ask because oh, and they want to show it off. In that case, just tell me you did good. Like just tell me, hey Sarah, I got a 90, and then I'd be like, oh my god, that's so great, I'm so glad. And then I could be happy for you without being sad for me. I'd rather not discuss that information. I like when we debated, like just not going. I was like, I kind of need to go. You should go see if we can go over it. Yeah, it's exactly why I was like, if he goes over it, I want to like take notes on my notes. But if he isn't, I'm writing it. That's future Sarah.
I was like, nah.
That was but I did I was like,
Don't be told.
it's the first one, so I felt like I don't know.
Get a little shout.
Yeah.
And my fluids, I got like slightly above the average. The average was under the bus. Well, no, I'm scared. Somebody got a 33 out of 30. So
33.
yeah, there's extra credit. There is.
Did they curve it?
No, there's just this strong disconnect between my major and my minor. Because yesterday I was talking to my friends and my minor, and this guy was like, "Oh, one of my classes on Zoom. I didn't do anything. I have a 97," and I was like,
Okay, but the fact that you're saying that out loud.
All right, everybody, I think I'm gonna go ahead and bring this back together here again if I could. Again, great job on the group work this morning. I hope that those are helpful exercises for you guys to reinforce what we've been covering. If you didn't get a chance to totally finish the group work, of course, the solutions are in Canvas, and the handout themselves are in Canvas, So for sure, you can look these up later, and I encourage you to do so. It's great examples to practice on. But hopefully we kind of got the idea of that. I want to kind of try to finish up on chapter 4 today by covering this one additional section. I happen to have a YouTube video about this. I think this is the exact title of it, which turns out to be one of my most popular videos. I don't know why, but I have lots of people have watched this video for some reason about subspaces that are associated with a matrix. So if I give you a matrix A, which is any size m by n, then I can associate some subspaces with it. There's 3 of them in particular that I want to mention. The first one we've already talked about, so I'm not going to say a lot about it again right now, but the null space of A, right? That's just the vectors in Rn, I'm calling them X here, such that this system of equations, A times X is equal to 0. And again, I verified in one of my videos a while back that that's always a subspace. And it's a subspace of what? It's a subspace of Rn. Rn. So we can find a basis for it. Anytime you have a subspace, you can find a basis for that subspace. So it'll have a dimension. Actually, we just talked about the dimension. What did we call the dimension of the null space? What was the word that I introduced about 20 minutes ago? The nullity, right? So this thing has a dimension, which is the nullity. So I think we're good to go on this. To find the basis and dimension, you just do the EROs and circle your pivots, set up free variables, solve by back substitution. We've done that all before. Okay, I want to focus more on the second and third subspaces here. So let's do number 2 first of all. This is and this is new. So this I have not talked about before. This is something called the row space of A. The row space of A. So let me tell you what I mean by that. The row space of A, by definition, actually all of these are definitions. By definition, the row space of A is simply the span of the row vectors of the matrix A itself. It is simply the span of the row vectors. Okay, so in a minute, I'm going to come back to that example that we had up here before. I'm going to just use the same example again. So capital A was just the matrix. What was it? 1, 2, 6, 2, 1, 6, 0, 1, 2, and 1, 0, 2. Okay, so this will be an example we can look at in just a minute. With this example, I just point out again, this was a 4 by 3 matrix. And so the null space was a subspace of R3. My question here is, well, I have 2 questions for you. The first one is, since it's called row space, that suggests that it would be a subspace. Can somebody tell me why it would be a subspace? Why would the row space, and keep in mind, I've said almost nothing about it so far. But based on what little I have written on the board about what the row space is, can you give me a reason why you know that it's a subspace?
It spans.
Because it is a span. You remember this? Earlier in the chapter, we made this huge point over and over that anytime you take the span of anything, it's automatically a subspace. You don't have to wonder about that any longer. So this is definitely a subspace. But what I also want to try to clear up here is subspace of what? So I want to know whether it's what we think it is here. Does anybody have a idea what it might be? And if you need to, you can look at my example that's sitting there. If I took the row vectors, by the way, the row vectors are just, you know, these rows, right? We're just saying the span of these rows. Anybody have a thought about what those vectors would be? Remember, when I say it's a subspace of R whatever, I'm just saying there's that many slots in the vectors. Yeah.
Is it subspace?
So R to the M is one very reasonable choice. What would be the other reasonable choice? R N would be the other reasonable choice. RM or RN, and I want to know which one is correct. Look at this example. M is 4, N is 3. If I look here at these rows, how many slots are there in each row? There's 3. The 3 was actually the N value. So this is actually a subspace also of Rn. It is a subspace of Rn, and it's a little confusing because the number of rows is the M value. I have 4 vectors here, right? So the number of rows is 4, but that's not what I'm talking about. I'm talking about the dimension of the row space, and that's only going to be it's a subspace of R3. Actually, we have to talk about what the dimension of the subspace is. Okay, so let me say something about that. Essentially, I lost my page of notes here. So in this example, the row space here, let's just write this here for the example. It is the span of the vectors 1, 2, 6, 2, 1, 6, 0, 1, 2, and 1, 0, 2. That's the definition of what the row space is. Now, I'm wondering if anybody has a guess as to what the dimension of this row space is. Keep in mind that this row space is a subspace of R3, and so I would not expect the dimension to be any more than that. Which is a little weird because I see 4 vectors here. So a popular wrong answer to what the dimension of the row space is, I'll hear students say, oh, it's 4 because there's 4 vectors there. But we all know better than that, don't we? We know that, you know, these vectors might not actually be a basis. They are a spanning set. They span the row space of A almost by its very definition. But what's the problem with having 4 vectors in R3? Goes back to earlier today.
It's not linear.
It's not going to be Li, right? When K is bigger than the dimension of whatever world you're in, then not Li, right? That's from the recap today. So if I have 4 vectors in R3, forget it. They're not going to be Li, and if they're not Li, then they're not going to be a basis. So here's what we're going to do. Actually, to get the basis for this, we're going to bring this matrix into, do it down here. I'm going to do those EROs. Actually, we already wrote down a row echelon form a little bit ago. It's already in your notes. I'm going to bring this matrix into row echelon form. And this was the row echelon form that I had come up with. Okay, so this is my row echelon form. And it turns out that your basis, okay, so let's just say it this way. as you do EROs and you replace, you sort of, as you do EROs, of course, you're changing the rows. But you're actually not changing the span of those rows. All of the linear combinations of those rows. It turns out, guys, that the span of these 4 rows is the same as the span of these 4 rows. But the big difference is that in the second matrix, I can clearly see that those rows of zeros should be removed from a basis. You never want to pay $1,000 for a 0 vector to be in your basis. So the basis here, my friends, the basis for this row space is just the pivoted rows of the row echelon form. You take the pivoted rows only. So a basis for, this is just in general, a basis for the row space of A consists of the pivoted rows, only the ones with pivots in them, the pivoted rows of the row echelon form of A. I'm sorry to write this so far down on the board, but it just fits right there perfectly for me. So you take the pivoted rows of this row echelon form. So in this example, a basis for the row space of A is the vectors 1, 2, 6, and 2, 1, 6. I'm sorry, 1, 2, 6, and 0, 1, 2. The pivoted rows of the row echelon form. That's better. Okay, are we kind of following that? Just the pivoted rows. What I'm saying here, guys, is pretty easy. If I give you a matrix and I ask you to find a basis for the row space, which is the span of the rows, all you have to do is bring it into row echelon form and keep the pivoted rows only. By the way, any rows that are not pivoted are going to be just all zeros. And you would never put those in a basis. So of course, we're throwing those away. We're only keeping the pivoted rows of the row echelon form. Marco.
I forgot when you did a whole going through EROs, but in this case, vector 0, 1, 2.
Uh-huh.
Is that the original one? Is that?
Well, I could permute these 2 rows to put the 0, 1, 2 on the second row, and then start massaging out the third and fourth rows, and they become all zeros. So it doesn't really matter which way you think about that. This is coming from the original matrix.
So
yeah,
the row space, the basis for a row space, we use the original vectors, or
the basis for the row space is just these 2 vectors.
but those are the original, like from the original A matrix. It's not after we perform the EROs.
Well, I would say it's after we perform the EROs. Let's think of it that way. So notice what I said here. The basis for the row space is the pivoted rows, not of the original matrix, but of the row echelon form of the matrix. So you should bring the matrix into row echelon form. In this case, it happens to be that the rows that you're left with actually did appear in the original matrix, but they wouldn't have to appear in the original matrix. Right. So by the way, guys, just so you're aware, this also tells me that the row space of A could just as easily been spanned by just those 2 basis vectors only. I only need to spend $2,000 to span the row space of that matrix. Even though I started off, it looks like I'm going to spend $4,000 to create this spanning set. It turns out that through the use of EROs to sort of expose the bad rows that get zeroed out, right? After I've done those EROs and exposed those bad rows, I'm left with just the good stuff, right? The actual vectors that are going to make up my basis are what I'm left with. See what I mean? And I'll just point out here that the dimension of the row space. What is the dimension of the row space here? It's 2, right? I have 2 vectors. What's it going to be in general? One more time.
Right.
The rank
of the matrix. Exactly, right? The pivoted rows. How many pivots do I have? That's called the rank of the matrix. So the dimension of the row space of a matrix is always just equal to its rank. So there's not a huge amount of content here, guys. Somebody hands you a matrix. You obviously can write down in the rows of the matrix, take their span. That's what the row space is. But if you really want to get a basis for that row space, you just need to bring the matrix to row echelon form and keep only the pivoted rows and let everything else go. The everything else being, the rows of zeros at the bottom. So you let those go. Your basis is just the pivoted rows. How many rows are going to be pivoted? Exactly that many, whatever the rank of that matrix was. Okay, so it's interesting, both the null space and the row space, they are both living in the same big universe. They're both living as subspaces of Rn, but they don't have the same dimension, do they? Right? The subspaces don't have the same dimension. The row space only has this dimension, whereas the null space had a dimension which was the nullity. And the rank and the nullity are two different numbers. We did learn earlier today that the rank plus the nullity has to add up to n, which is the number of columns. But like even on this example, which we did earlier, the nullity was only 1, and now the rank is 2. 1 plus 2 adds up to 3, which is the number of columns. So we're just playing around with some basic concepts with these matrices here. Questions on this? Okay, let me go on to the third subspace. Anybody have a guess what it's going to be? The column space. Exactly. We just did the row space. I got to do the column space. And this is usually just written call space. So the call space of A, by definition, as you probably realize, this is just going to be the span of the set of the columns of A. I should say column vectors of A, just to be precise. It's the span of the set of the column vectors of capital A. And does anybody have a guess as to what the column space would be a subspace of? Rm, right? So in this example, we see that each column has 4 slots. The 4 is coming from the M value. So this is a subspace that lives in a different universe than the null space and row space do. The null space and row space both live in Rn, but now the column space lives in Rm as a subspace of it. I'm not saying that the dimension of the column space is M, right? Just the dimension of the big universe is M. The column space is a subspace inside of that, which actually could be smaller. Right. So let's actually talk about how you get the column, the basis for the column space. So here I have 3 columns, right? And the question would be, how would you get the basis for those? So there's an easy way to do that, which I'm going to write down here. Again, it turns out, what you're going to do, so let's go back to this same example that we had before. So I'm going to write down this matrix one more time. 1, 2, 6, 2, 1, 6, 0, 1, 2, and 1, 0, 2. And I'm going to once again imagine doing the EROs. So again, I'm going to just recopy one more time the same row echelon form that we had before. And I'm going to circle my pivots again. And if I want to get a basis for this, for the column space, so a basis for the call space of A, you might think that I'm just going to take the pivoted columns of the row echelon form. After all, to do the basis for the row space, all I have to do is take the pivoted rows of the row echelon form. So you might think that to get a basis here,
that I would just take these two pivoted columns. But it turns out it's not quite that easy, because when you do EROs, you're messing with the rows, right? You actually are kind of screwing up the columns as well. I'll give you an example. If I took this matrix right here, and I asked you, what's the span of the columns? You probably would realize that this is the basis of that. Because after all, it's just the same column twice. So the span of the columns is literally just going to be any multiple of that. But if I do an ERO real quick, I'm just scribbling over here. You don't need to really write this down. I just want you to kind of observe this. If I just do this ERO where I kind of zero out the second row, and then I ask you, well, what's the column space of this? Well, you would say that the basis for that would be this vector. Because the two columns, they're still the same. But the issue is the span of this is not the same as the span of this. Right? It's pointing in it's a vector pointing in a different direction now. So EROs have this bad habit of messing up the column. And so I can't just take the pivoted columns of my row echelon form and assume that that will be the basis for the column space of the matrix I started with. But it turns out it's an easy fix. I'm not going to prove this today. This would be more of a Math 307 thing. But what you do here is you take, so this consists of the columns of the original matrix A. You have to go back to the original matrix before you screwed it up with the EROs, right? You go back to the columns of the original matrix A corresponding to the pivots. So the pivots are still relevant. I have two pivots here. But what all this chit chat explains right here basically is just that you take those pivoted columns, but then you transfer back to the corresponding columns from the original matrix. So in this example, so here, a basis for the call space of A would be the set, I'm going to make it as a list of vectors here, the first column and the second column. That would be my basis. And let's also write down the dimension of the column space. So as a little note here, the dimension of the call space. Can anybody tell me what they think that formula might be? That's also the rank, isn't it? Yeah, that's also the rank, because again, it's really just coming down to the number of pivots. That's how many vectors are going to be written down. So this is also the rank of A. This is also going to be the rank of A. Absolutely right. Absolutely right. So it's interesting. This is a little bit confusing. It's interesting that the null space and row space live in the same universe, but have different dimensions, right? The rank of A for the row space, right? The row space is rank of A, the column space is the nullity of A. They live in different universes, sorry, they live in the same universe and have different dimensions. But the column space lives in a different universe altogether, Rm rather than Rn, but yet its dimension is the same as the dimension of the row space. Both of these are rank of n. Now, if this feels like it's a lot to kind of keep track of, I've pulled up my Canvas page here. I'm going to go into the file section and just show you something really quick. There is a special handouts folder. A while back, I wrote up this thing called Recap for 4.6, 8, and 9. I'm gonna open this up and show it to you here. And this stuff at the top is just reminding you about what a basis is. Spanning sets, Li. If K is bigger than the dimension of V, less than the dimension of V, or equal to the dimension of V, those are the 3 cases that we did in the group work today, right? We practiced earlier. But what I'm talking about right now is actually this thing down here at the bottom half of this handout. It's just a handwritten thing I did a while back that has turned out to be kind of old for people in this class to try to learn this stuff. I've got my null space, row space, and column space here. I wrote down what those spaces are. Okay, and which one they're a subspace of. Is it Rn or is it Rm? Right, and then what the dimensions of them are. So we have nullity, rank, and rank. And then finally, the last column is, well, how do you get a basis for each of those things? The nice thing over here in the how to find a basis category is that for all 3 of these subspaces, you notice that for all 3 of them, you just do the same thing. You just need the row echelon form of A, right? When we took this matrix and I asked you, what is a basis for the null space? We did EROs on it. When I asked you what is a basis for the row space, we did EROs on it. And when I asked you what a basis is for the column space, we did those same EROs on it. And my point is you don't really have to do it 3 times. You just do it once. You find the row echelon form one time. And once you've done that, you'll be able to find the basis. In the case of the null space, you have to bust out the free variables, right? In the case of the row space, it just says take the pivoted rows of the row echelon form. And in the case of the column space, it says take the columns of A corresponding to the pivoted columns of the row echelon form. So it's basically exactly what's on the board here. So if you didn't take notes for the last 10 minutes or something over there, this handout is a beautiful summary of everything you need to know from what I've just been talking about. And it's just all in one place. And so it's kind of nice if you're trying to keep these things straight to take a look at that. Okay. Are there questions on this? Yeah, so this is just to remind everybody, there's a folder in here. Close that up. It's called special handouts right here, right at the top. You can see special handouts, which is in the files section. And it's just recap of 4.6, 4.8, and 4.9. Okay. If we're good with that, I have just one last thing I'm going to do today, which is a really nice way to kind of wrap up chapter 4. I would like to revisit a very, very important theorem that we've been working on for a long time. And we're going to come back and say a little bit more about it here. And this is really in another section. This section, it's not much to it. Pretty much just write down this result. I want to revisit this famous invertible matrix theorem. You guys remember this one? I like this theorem because it helps us put everything together conceptually. This is totally a conceptual thing. But just to remind you, we have A, which is an n by n matrix. So we have n rows and n columns. And then what we had was the following are equivalent. Remember that? And this is the theorem that has the big long list, the list of things. So you might remember the first thing in the list is just that A is invertible. Now, I'm not going to write down all of the things in the list that we've already done, but I'm going to write down a couple of them because they're going to be actually relevant for what I'm about to do with this list. I'm going to jump to C real quick. I'll skip over B. What C said, if you have the list of the invertible matrix theorem, is that if you look at the system AX equals 0, that has only the solution x equals 0. So if you create a linear system with the coefficient matrix of A and you set this equal to 0, see if A is invertible, you can basically cancel it. And so when you cancel it, you solve for x and x is just 0. Okay, another thing that was in our list already was the rank of A. The rank of A, you might remember that was supposed to be equal to n. And then we go down the line a ways. We had done G. I think that's where we left off. The G was just that the determinant of A is not 0. So everything that we have written down about this theorem before is kind of, these are some of the highlights from this theorem. Remember, for a given matrix, all of these things are true about that matrix, or they're all not true about that matrix. And what I would like to do right now is add H, I, J, K, L, M, N, O, and P. Do we have time? I think so. We're going to add a whole bunch more things. Okay? This is going to enhance this theorem. It's going to enhance the theorem and hopefully enhance your overall understanding of some of these more recent concepts. So let's see how well you guys can do with this. I'm going to do number H here. Item H. Start with something that's not too bad. Item H is going to be about the nullity of an invertible matrix. So let's just remember the nullity is the dimension of the null space. And so it's however many free variables you have. Does anybody have a guess as to what the nullity of an invertible matrix would be?
0.
Can somebody remind me what the rank nullity theorem said earlier today? This is a really big theorem we wrote down. Remember what that theorem said?
The rank of A.
The rank of A plus the nullity of A. What was that equal to? N, right? Does that help? Blake?
So the nullity of A is equal to rank of L?
No. Gilbert?
N minus 3.
Yeah, and what is the rank of A if A is invertible? The rank of A is n, so the nullity would be 0. The rank plus the nullity has to add up to n. So guys, if an invertible matrix has full rank, then it actually has nullity of 0, right? So for an invertible matrix, the nullity will be 0. It just means that there would be no free variables when you row reduce an invertible matrix. That's not surprising. That's not surprising. Okay, so I don't know if I've ever talked about what it means for something to be 0-dimensional. Because after all, this word just means the dimension of the null space. If something is 0-dimensional, it basically means that it is 0. It doesn't have any basis of any substance to it. Right? There's no basis vectors you can make, so you really don't have a space there, right? So the next item is sort of speaking to that, and it just says if you have an invertible matrix, the null space of that matrix is literally just the 0 vector. There's nothing more to it. There's nothing more to it than just the 0 vector itself. Okay, does that make sense? So if A is invertible, it has a tiny null space. A tiny null space, as small as it could possibly be. Just literally 0. Okay, let's keep going here. The next statement, J, is about the columns of the matrix A. Well, the columns of this matrix, so, by the way, this is just another statement here that says that the null space of A is 0. If you solve this system of equations, right, AX equals 0, right? What are the solutions to AX equals 0? Well, there's only one vector that's in that null space, and it's that vector. But the other thing is, if I wanted to find whether the columns of A were Li or not, I would lay them into the columns, well, I'd write out the matrix A and augment it with 0. And I would solve it and there would be only the trivial solution. So this actually means that the columns of an invertible matrix are for sure going to be Li. They're for sure going to be Li. Remember, just in your minds, guys, when you're thinking about an invertible matrix, I want you to imagine pivots going right down the main diagonal, all the way down from the upper left to the lower right corner. There's no free variables there. No free variables means Li. Okay, let's keep going. The next one is, what about the call space of an invertible matrix A? Well, if you believe what I said a few minutes ago, this is kind of what an invertible matrix looks like, right? Columns look like that. What does it say about the column space? Find a basis for the column space. Take the columns of the original matrix corresponding to the pivots. Well, every column has a pivot. If A is invertible, that would be every column of A. And that would be n of them, right? The rank is n. Well, the only n-dimensional subspace of R, by the way, in this case, this is also an n. The only n-dimensional subspace of Rn is Rn itself. It's the full Rn. It's the whole thing. So an invertible matrix has a tiny null space and a massive column space. It's as big as it could be. You can't get any bigger than the full big universe that your columns are living in. All of your columns are living in Rn, and you're saying that the span of those columns is the entire universe. That's huge. Okay, so real quick, we're almost done. If my columns are Li and they span the whole Rn, then they form a basis for Rn. Exactly. So let's write that down as well, guys. Columns of A form a basis for Rn. Right? And now finally, I'm going to do M, N, and O. By the way, these are all good things, right? It's good to have a basis. It's good to have full rank. It's good to have an invertible matrix. The next three statements, since I'm out of time, I'm just going to write them down. Basically, the same three things for rows are also true. So the rows of A are Li. The row space of A is equal to Rn. And the rows of A form a basis for Rn. Okay, there's no M here because this is an n by n matrix. So everything is just an n. All of these things go along with having an invertible matrix, all put together. Guys, that's it for chapter 4. Any questions on that? So I need to tell you one quick thing before you go. I have some homework that I think is assigned for tomorrow. I think I'm going to let you work on that a little longer, if that's okay. So I'll be extending that probably, especially because I don't know exactly where I'm going to be tomorrow. So I'm not quite sure that tomorrow's a good deadline for that. The other thing is, you remember how I had you watch a video for extra credit for the first midterm? I'm probably going to have one of those for you again for the second midterm. Are you guys on board for that? Yeah. Is that a good idea? Yeah. It might be this weekend. Is that okay? You can do it. Okay. So I will send you an email by tonight with kind of the new deadline for this homework and maybe a video to watch. Thanks, guys. Have a great rest of your day. Have a great day, Eduardo.